And they're saying that our delta CH, so that'd just be our combustion, and this enthalpy is changed to be negative 483.6 kilojoules. Our oxygen would be equal to negative 483.6 kilojoules. However, our hydrogen would be different. And all we're saying is that our delta CH is equal to N times delta CHM. And we're dividing it by the amount of moles by our enthalpy change. So we're dividing, for hydrogen, we'd have to take negative 483.6 kilojoules and divide that by 2. So you just divide it by 2, which would give us our molar enthalpy of hydrogen gas, which would be equal to negative 483.6 divided by 2 is equal to negative 483.6 divided by 2 is equal to negative 241.8 kilojoules. And that would be the same as H2O. Is that liquid? I didn't put it. Gas. Since our moles is the exact same. We'll do another one for B, which has a lot of different moles. So B says 4NH3 gas plus 7O2 gas forms to react 4NO2 gas plus 6H2O plus 1272.1 kilojoules. So, similar to how we showed above of our communicating enthalpy change, they're writing it as a product. So, all we know that it's the same way as saying our delta, our H, if you'd like to think about it like that, our delta CH is equal to negative, since it's on the product side, 127.21 kilojoules. To find each reactant or product's molar enthalpy in this combustion reaction, we'd have to, once again, divide our moles, or delta CH, by our moles to show our molar enthalpy. So for NH3, we'd go negative 127.21 kilojoules divided by 4. So just be negative 1272.1 divided by 4, which would be negative 1272.1 divided by 4 is negative 318.025 kilojoules. So all it's saying is for every 1 mole of NH3, negative 318.025 kilojoules of energy is being released because it's exothermic. For oxygen, it'd be divided by 7. NO2 would be the exact same as NH3 since they have the same moles. And H2O would be divided negative 1272.1 divided by 6. Now we're going to get into Hess's law. Starting on page 505 in our chemistry textbook, looking at question 2. It says, calculate the standard enthalpy change for reaction 1, the gasification of coal from the following chemical equation and standard enthalpy change. So, in Hess's law, Hess, as chemist, discovered that if we took elements in a few compounds, or elements inside making compounds, we could try to make whatever kind of equation we need to find and use these basic tools and manipulate it so that we can go and find our molar enthalpy or enthalpy change of any reaction without actually doing it. And so, in number 2, we take the combustion of carbon and the combustion of hydrogen. And so what we're actually trying to find is so if we look up above, it actually shows us what we need to produce. So it would be H2O. This is in figure 5 if you look just above. It'd be H2O gas plus C solid forms through reaction carbon monoxide gas plus hydrogen gas. And we are to find our enthalpy that we don't know. So taking these basic elements like the combustion of carbon and combustion of hydrogen, we're able to find out our actual enthalpy change. So H2O, we realize we have to put it on this side. Now, looking at question 2, we'd realize that we would have to reverse a reaction of H2O to get it on the reactant side, because that's what we need. So we're going to take 2 and also divide it by 2, since it already has 2 H2O. So if we were to divide it by 2 and reverse it, we would have to take our enthalpy formation, so these formations, and so we'd have to, if we are to reverse anything, we reverse the sign by going negative. And if we're to divide it by 2, we'd also have to divide it by 2 here. So we take 2H2O and make it H2. So we're reverse, divide by 2. H2, 2H2, or now just 1, plus 1/2 O2 gas to form H2O gas. Now to reverse it, that would be just negative 483.6 kilojoules divided by 2. To reverse it, now all we're doing is going H2O gas forms H2 gas plus 1/2 O2. Delta RH is equal to negative 483.6 divided by 2, equaling to 241.8 kilojoules. For our second part, so we have 2 formations. Somehow we have to get carbon on this side, and it's already there, but we only need 1 mole of it, whereas in this question we get 2 moles. So we'd have to, once again, divide by 2. That's a really crappy divide sign. So that would be C solid plus O2 gas, or 1/2 of it, to form 1 mole of CO2 gas. And now we'd have to take our delta RH, which is negative 221.0 kilojoules, and divide it by 2, which is equal to 110.5 kilojoules. Now what you do is see what cancels. So you look at this side and you look at this side and see what occurs on both sides. So we'd see that our oxygen gas, 1/2, is on both sides, and we're left with just what we need. So H2O gas plus C solid forms H2 gas plus CO2 gas. And now, oh sorry, we forgot to change our sign in the second part. So when we reverse, if it's a negative, we make it a positive, and if it's a positive, we make it a negative. We just change the sign once we reverse it. So we'd realize that 241.8 positive plus negative 221.0 is or 241.8 plus negative 110.5 is equal to our delta RH of 131.3 kilojoules. Positive, meaning it's an endothermic reaction. Using Hess's law, we can determine if any reaction is endo or exo by calculating it. Along with, we can figure out what our delta RH is of any reaction. If we look at number 4, I'll do this one less choppy. It says, calculate the standard enthalpy change for reaction 3, the methanation of coal gas, using the following information. So looking above, it says we need 3H2 gas plus carbon monoxide gas to form methane plus H2O gas. And we're to find our delta RH of this reaction by using these basic stones. So, for our first part, all we're going to do is look at how can we find H2 gas to be on this side. And in our first reaction, if you look at number 4, our first formation, we see it right there. However, we need 3 moles instead of 2, what is inside the formation. So all we'd have to do is realize that we'd have to times it by 3/2, that reaction. So 3H2 plus 3/2 O2 gas form, sorry, we cut off 3/2 O2 gas. And lastly, we have 3/4, or that's 6/2 H2O